Hello and welcome back to Dynamic System Modeling. In today's session, we will be discussing how to obtain the differential equations or the mathematical model of electrical systems. Electrical circuits are driven by flows. As an analogy, we could see that the water flows downriver due to change in height. In general, circuits are made up of three main components, which is the voltage source, the conducting element, and the resistance. As an analogy, we could use this container. So the amount of a fluid in this container is equivalent to the amount of charges inside this battery. And as the amount of charges increase, the voltage will increase. And the voltage is the pressure exerted by the fluid at the end of this hose. And therefore, as the amount of charges increase inside this battery, the amount of pressure or flow of electrons will increase. And the conducting wire is the hose. The resistor, in this case, can be thought as a rock, as putting some rocks inside this hose, okay, which resist the flow of the fluid, right? And this is called the resistance. Resistance is like the material. You increase the amount of material, density of material at this location in which it resists the flow of electrons. Now, if you are given an electric component, you should be looking over the voltages across its terminals. If this is the positive, this is the negative side, E1, E2, then the voltage across this electric element is given by E1 minus E2. It is the same as we did in the mechanical components. This is mass M1, this is a spring of stiffness K, M2 you have a force, okay. You put certain references, right, x2, x1, then you obtain the force across this element as, okay, k x2 minus x1. So you look over the terminals of this component. You say x2 minus x1. And the same should be done in electrical elements. And this is the most important thing you should remember. Now consider the first electrical component, which is called the resistance. Then the voltage is equal E1 minus E2. Okay? So what is R? Again, R is the resistance. It's the model of a physical component. Interestingly, Ohm's law states the following: E equal R I. What Ohm's law is telling us that if a voltage is applied across a physical component and the current is passing through it, all what you should look over this component is the resistance. No matter color you have, okay, no matter shape what you have, no matter what is the smell, only we are interested over those elements is the resistance. So we can eliminate the physical component itself and replace it with R. And then we can use it in Ohm's law equation. Okay, we can model the components. So the model of this equation, of this physical component, is voltage equal Ri. We are interested in only one constant, regardless of its color, regardless of its shape, and so on. Alright? And the same thing is as we did in the mechanical component, that the Newton's second law states that the summation of forces is equal to mass times acceleration. Again, we are interested only on one constant term, which is the mass. Like the table, you have the car. No matter what you are studying, you are interested only on one physical property of the element, which is the mass, regardless of its shape, of its color, and so on. So we can apply Newton's second law. Okay. Alternatively, we can say E is equal to E over R. Let's take another electric element, which is called the capacitor. And this is the voltage, again E1 minus E2. Then the property that we have is IC equal CDE, the voltage across the capacitor by dt. Remember E, the voltage is E1 minus E2. If we have the inductor, okay, I equal, this is E, equal LdI by dt. Now, if we would like to look over a certain interval, okay, we could integrate both sides, like from 0 to time t. Okay, we can integrate from 0 to t, get dt. Then 1 over L, you can bring this constant outside. The integral of I, di, sorry, it is I, bounded between time 0 and t, okay, which is I of t minus I of 0. Then I L of t is equal to 1 over L. Okay, let's have an example. Okay, now we want to derive the model of the circuit below. You can use KCL, KVL, node equation. Let's start by KVL, the Kirchhoff voltage law, or the voltage. Maybe you can use even the summation rule of voltages. So we can say E, the input, is equal to E, the capacitance, the voltage, is distributed over those three electrical components. EL. Now we want to define the input and the output of the equation. Let's assume this is the input, okay? This is the input EI, and the output is, we are interested in studying the current across this circuit. So the output would be I, the flow of the current. Now we should replace EC by the voltage of the capacitor by the current passing through the capacitor, the voltage of the resistance by the current, because we are interested with the current, right? So we can say E of the capacitor is E what? Okay, we know I of the capacitance is equal to C d EC by dt, right? Now we can look over a certain time interval from 0 to t. Okay, we can integrate from 0 to t. Then 1 over c. So the integral of the derivative, this could cancel this, okay, bounded between 0 and time t. Okay, the current IC is the same as I. Okay, the current passing through the capacitor is I. So EC is 1 over C I dt plus E of 0. The voltage across the resistance is Ri by Ohm's law. Again, the current is passing the same as I. EL is equal to L di by dt. Great. So we obtained the input-output equation, right? So we have the input EI and we have the output I. Great. This is the input and the I's are the outputs. Those C, R, and L are some constants representing the electrical elements. Okay. Now, if we want to obtain the differential equation and to eliminate actually the constant term, the integral, we can derive the whole equation, both sides. EI dot derivative of the integral is derivative of this term is 1 over Ci plus derivative of E0 is 0 R I dot plus Li double dot. I wrote the I in a capital term just not to confuse between the derivative. So I mean by I double dot, it is d square I by dt squared. Okay, now we can rearrange the equation. So it is the same as the mechanical component, like mx double dot plus px dot plus kx is equal to f. Okay, in this case f dot, right? The input. Okay. Let's take another example. Now we have the current. Let's assume the input is the current. And we are interested in the output of studying E0. Then we can apply KCL, Kirchhoff current law, and I, the input, is equal to I, the capacitance, IR, IL. Because we are interested over E0, okay, the voltage, so we need to replace those components into voltages. The voltage across the capacitor is E0, across the resistor is E0, and across the inductor is E0. Why? Because those are in parallel, right? And we know that the voltage is the same. E0 over R and the current across the inductor is equal to what? If we have EL equal LdI by dt, again you can study across a certain time, okay, because you will apply the current like for a ranged period of time of your choice, 0t, 0t, okay, then 1 over L. The voltage across the inductor, okay, is E0. To eliminate the constant term and the integral, we can derive the whole equation. Again, I will be writing this as a capital, not to confuse with this small I, okay, the dot over the small I. So this is the differential equation governing the electric circuit. In summary, any element you have, you should be subtracting in order to obtain the voltage of any element, you should be subtracting the voltage across its terminals. In this case, E1, E2, then voltage equal E1 minus E2. The current across the resistor is E over R. The current across the capacitor is CD, E by dt. And the current across the inductor is the initial current at time 0 plus 1 over L integral of voltage by dt. Why I wrote those in this format? Because I'm interested actually in the node method, which is a combination between KCL and KVL, make things easier for me to solve or to obtain the differential equations of electric circuits. In the upcoming session, we will be discussing the node method that I'll be using throughout the whole explanations of the upcoming lectures. And thank you.